Hello everyone, my name is Chirag Patil and welcome back to my YouTube channel. So in today's video, we will explore a DenseNet in detail and we will implement it using PyTorch. Okay, so let's get started. So first of all, DenseNet is a short form for densely connected convolutional network and it was introduced in 2017. And this architecture was presented at the IEEE conference on computer vision and pattern recognition, and it quickly gained the recognition for its efficiency and performance. We will see in the paper how efficient it compared with another model, right? And it achieved competitive result on datasets such as CIFAR 10, CIFAR 100 and ImageNet. Although it did not directly win the major competition like ImageNet, but achieved the result which are comparable or exceeding the ResNet in some tasks, right? And it is also parameter efficient. Okay, so let's see why it is or what are the major idea of DenseNet, right? So the central idea of DenseNet is to ensure maximum information flow between the layer of the neural network, right? And this can be achieved by connecting each layer directly to every other layer in forward fashion. We will see in diagram and code how these connections are happening, right? So if you see in traditional convolutional networks, each layer has connection only to its intermediate preceding layer, right? But DenseNet create direct connection between any two layer with the same feature map. Of course, when we need to use previous output as well, right? So they both should be in the same size, and we had seen this in InceptionNet and ResNet as well, right? So if we have DenseNet with L layers, there will be L into L plus 1 divided by 2 direct connection in total. So each layer takes the feature map of all previous layers as an input and pass it on feature maps to subsequent layer, right? So let's understand what this basically means, right? So this is the basic diagram. So first of all, if you see in the ResNet, we had learned that it provide one skip connection, or you can say residual block, right? So what we are doing, we are passing the information from here to directly at this layer, right? Same DenseNet also saying this can be achieved by connecting each layer directly to every other. So if you see, this is something like that, right? We are connecting this layer output to directly at this layer, right? And InceptionNet block, what we were doing, we were having multiple convolutional block parallelly, and after that we are concatenating the filters. Okay, and now this diagram is basically a DenseNet. It is not the whole DenseNet architecture, but it is dense block. Okay, so if you see it, it is a combination of this residual block or inception block, or you can say it is very inspired by ResNet and InceptionNet. Okay, so let's see how it is. So first of all, this diagram is for dense block, and you can think as a one dense block can contain multiple convolutional layer. Okay, so let's say we are getting the input and we have one convolutional block. We will see how this convolutional block, batch normalization, ReLU and convolution basically, right? So what we are doing here, let's suppose this is generating some feature, this convolution layer generating some feature. Okay, so let's say the feature shape is 56 cross 56 cross 32, where 32 is number of channel, you can say. Okay, so the next layer will use this 56 cross 56 cross 32 and generate the output of same size, which is 56 cross 56 cross 32. But this next layer of this, you can see this purple block, will receive the output of this layer and concatenated output with this as well. So when this purple block will receive the input, it will be 56 cross 56 cross 64. The 32 from here and another 32 from here. So it will receive 56 cross 56 cross 64. So basically each layer will take an input of previous layer's output as well and concatenate it with own output, right? So now here also this yellow block will receive 56 cross 56 cross 96 because 332 features are concatenated at these layers, right? So this is how we are concatenating the output of each layer or passing the information from previous layer to each preceding layer, right? So one thing, we are skipping the output as well, And the second thing, we are concatenating. So you can think it as a like combination of inception net and residual block. And this skip connection or information passing will help DenseNet to reduce the vanishing gradient problem and pass the feature information to the next layer. Right. So now let's see the paper, and we can see some parameters here as well. Okay. So the diagram which we were seeing, it is taken from this paper basically, right? So you can see the 5-layer dense block. So this is basically one dense block which contains the 5 layer, and with growth rate of k is equal to 4. So what is basically growth rate? So growth rate you can think as the number of feature map that you will create or you will pass further. Okay. So it is nothing but, in simple term, you can think it as like an output of each layer. So if my growth rate is, let's say, 4, then each layer will create a 4 feature map. So in previous example, we were talking about 56 cross 56 or 32, right? But if your growth rate is 4, then you will generate 56 cross 56 cross 4. All layer will create a same shape of output, right? If they will not create same shape of output, we cannot concatenate them, right? So this is the growth rate. Now let's see. Yeah, this is the basically a DenseNet architecture. So there are 3 dense block here, but we will create 128 dense block. So basically DenseNet 128 it's called, as we are using like DenseNet 18, right? Same as like DenseNet 121 we will create in this video. So if you see the whole DenseNet, there is one convolutional layer, then dense block, then this is convolution and pooling. So basically it called as a transition layer, or you can call it as a compression layer as well. So whatever output is created from here, right? So it will reduce the number of channel for next dense block basically. It's called as a compression block or transition block. So you can say first we will apply convolution, then there will be the dense block, then this compression layer, then again dense block, then compression, and so on. At the last we will have average pooling and linear layer, which will predict our classes. Okay, so this is the DenseNet core concept. So now let's see the whole architecture here. Okay, so you can see this kind of table we had seen in inception block as well and ResNet as well, right? So let's see. First we will take the input of 224 cross 224 cross 3 channel RGB. Okay, so first we will apply the convolution with 7 cross 7 kernel size stride 2. So it will reduce the image shape by 2. So basically we will receive 112 cross 112, right? We will see how much feature we will require, or how much kernel or how much output channel we will use. Okay, the next we will apply the max pooling with 3 cross 3 kernel and stride 2. So it will again reduce our size, so we will receive 56 cross 56. After that we will have dense block. Okay, so dense block will contain a multiple layers, and one layer is nothing but, you can consider it 1 cross 1 convolution followed by 3 cross 3 convolution. Okay, so why we are using 1 cross 1 convolution here? So we had seen in inception net as well that 1 cross 1 convolution help to reduce the number of channel or number of feature map size, right, with parameter efficient way, right? So first of all we will reduce the feature map size using 1 cross 1 convolution, then we will apply 3 cross 3 convolution, and we will get desired feature map shape, right? So this is one layer of DenseNet, dense block, and we will use such a 6 layer. Then we will have one transition layer. It is nothing but 1 cross 1 convolution, which will reduce the number of channel, or you can say feature map size, and after that we will apply average pooling, which will reduce the size from 56 cross 56 to 28 cross 28, right? And so on. We will have dense block of 12 layers, then again compression layer, then 24 block, then compression layer, and then 16 block. So if you see, this called as a DenseNet 21, here 169, 201 and 264 total. So how these 121 layers are calculated here? Okay, so let's see. Here we have 6, 12, 24 and 16, right? So if you sum that, it will be at 58, right? And each layer contains two convolutional blocks, right? So if you see, let me write it here, okay? So if you see, let's say 58 cross 2 will be 116. Now you have this one convolution, 17, then 18, 19, 20, and last we have fully connected array which will be 21. So hence you have 121 convolutional block, or you can say 121 layer, basically not all the convolution, we have one fully connected as well, right? So you have 128 layers here, hence it is called as a DenseNet 121. And the growth rate for all network is 32. In the diagram they are showing k is equal to 4 for simplicity, but in paper they had used growth rate of 32, right? And they mention when they are saying conv layer, this one, it is basically first we will apply batch normalization, then we will apply ReLU, and then after we will apply convolutional block or convolutional operation, okay? So this is about the architecture of DenseNet, right? And let's see the comparison of this model with the ResNet they had provided. So we had seen like it is parameter efficient, right, and providing a better result than ResNet in some case. So if you see here, so this is basically 10 raised to 7, so you can consider as a 10 million, okay? So if you see here, the DenseNet 128 has a lower validation error with around less than 10 million parameter, right? Where the ResNet 34, which is very low layer network, you can say ResNet was start for ResNet 18, ResNet 34 and so on, right? So ResNet 34 having more than 26.5 error rate with around 20 million parameter, and DenseNet achieve the less than this ResNet 34 error using 10 million parameter. So we can say it is parameter efficient and providing a better result as well, right? Same as you can see DenseNet with 264 layer is performing better than ResNet with 152 layers, and parameters are very less. Here you can say 32 million kind of, and here we have 60 million parameters. Still we are not getting same accuracy, right? Same validation error. So this is why the DenseNet is parameter efficient, okay? Now they had shown some other comparison as well. So this is about the DenseNet. So now let's start the building the network, okay? So first of all we will create a block, and this particular block layer, you can say 1 cross 1 followed by 3 cross 3 is called as a bottleneck layer, and when you combine this multiple layers it called as a dense block. So now let's first create a bottleneck layer, okay? So let me write it here. Let's import some libraries. Let me write, okay, what is the issue? Yeah, I need to install this, right? So it will help to visualize the model at hand. Let me write pip install torch. Let's import now, okay? So now let's start. First we will create bottleneck layer, okay? Let's say bottleneck and dot module. Let's first create constructor. It will take self, and we will require in channel. I will explain what we are doing. Just let me write few lines and then we will go to the paper as well, like what they had suggested, okay? First of all we will require in channel, then let's say out channels, okay? Or not the out channel, growth rate. I'll tell you why, okay? This is basically a growth rate. Let's call super bottleneck provide self and call the init of it, okay? So now it's ready, okay? So first of all we had seen that when they are saying con, it is batch normalization, then ReLU, then convolution, okay? And as I told you, right, when they are saying growth rate of 32, so now it will create the output in the 32 channel basically, right? And the second thing, let me tell you one another thing. Okay, so here, so in the bottleneck layer instruction, they had mentioned what they are using. They are saying we let each 1x1 convolution to produce 4K feature map. So 4K, basically K means the growth rate, and they are creating 4 into growth rate feature map. So basically, when you write this 1x1 convolution, this will reduce or create a feature map size which is 4 into growth rate. So for example, our growth rate is 4, then the output of this 1x1 convolution will be 56 cross 56 cross 16, because 4 into 4, which is growth rate, right? And 3 cross 3 convolution will create the output as a growth rate, because we need to concatenate in the next layer, right? So now let's implement that. So first of all, let's say we need to provide self.batch normalization, right? Because they had mentioned here the each con block is first batch normalization, then ReLU, then convolution, right? So first we will create 1x1, then we need to create 3x3. So same, let's say batch normalization 1 will be nn dot batch norm 2d, and it will take in channels output, right? The input of this batch normalization layer will contain this much channel basically. Then self dot, we need to use con block, right? Let's say con 1, which will be 1x1, right? So let's say nn dot con 2d, and it will create the in channels, and the output of 1x1 convolution will be 4 into growth rate, right? So we will use this growth rate here. So let me write 4 into growth rate, because they had mentioned they are using 4K, right, for the 1x1. So here kernel size, let's say it will be 1, right? And now we need to create 3x3. So let me write here, it will help 1x1. Then let's create 3x3, right? So same we will apply self.bn2 will be nn dot batch norm 2d, and it will receive the output, or basically output of this convolution block, and it will contain this much in channels, right? And now it will create the output of number of growth rate basically. Okay, so let me write, it will be growth rate. So what we are doing here, we are reducing the in channels by 4 into growth rate, and now this will be the input of next convolution block, which will contain 3x3 kernel size, right? And this will, sorry, we should not write here. Okay, so next convolution block, which will has 3x3 kernel size, will create a feature map of size number of growth rate basically. So let me write self dot convolution 2, it will be nn dot con 2d, and it will, the in channel for this convolution will be 4 into growth rate, and it should generate out channel of growth rate, right? Basically 32 in our case. So that's why we can concatenate the previous input, right? So let's say growth rate, and then provide kernel size. Kernel size will be 3. We will use padding is equal to 1 basically here, right? So this is about bottleneck layer. Now let's define the forward method, right? So you will get the clear picture of what is happening in the bottleneck. Okay, so let's say forward, multiple self, let's say x. So first let's say out, or you can say x is equal to as well, self dot con 1, we need to apply nn dot ReLU, right? So let's say we will use f dot ReLU. We had imported f here, right? So let's say f dot ReLU, and then we need to provide the output of batch normalization 1 layer, right? So this will be x. So what we had created here, so this part, batch normalization, then ReLU, then convolution. So here if you see, we are applying batch normalization first, then ReLU, then convolution, right? Same we need to create a second self.con2d, sorry, con2, f.relu, and it will contain the self.bn2, and it will contain the output out, right? So till now this is nothing but simple the convolutional layer, right? So first convolution layer's output is going into next convolution, simple, right? And now what we need to create, we will concatenate this output or previous output with the current output, right? So let's write out will be torch.cat, we will pass x and out, right? So basically the input will concatenated with the output of this layer, and we will apply dimension is equal to 1. Basically a channel, it in PyTorch we have channel first, right? So the output here will be something like, let's say 32 cross 56 cross 56, right? And we are concatenating at the dimension 1, basically a channel, right? Let's return out. So here we had created a bottleneck layer. So you can see this layer we had created 1 cross 1 convolution, which will reduce the size into 4 into growth rate, and then we will apply 3 cross 3 convolution, which will generate the output shape of growth rate, basically, right? And this, the image shape, or you can say output size, will not change. We are just changing number of features, or you can say out channels, simple, right? So this is about bottleneck layer. So now let's create a dense block. So let's say class dense block, nn.module, define init, need to provide a self. It will also require how many layers we need to create, right? So basically one dense block will contain multiple bottleneck layer, right? So first we need how many layers this dense block will contain. Okay, so let's say number of layers, and then in channel, and then growth rate, same as this the bottleneck layer, because it will contain nothing but multiple bottleneck layers. Now let's call the super, it will be dense block. I'm passing here super dense block, then provide self, let's call the init of it, right? Simple. Now let's implement it. So first of all, the dense block is nothing but multiple layer of bottleneck, right? So let's say for I in, let's say range of number of layers, right? Now it would be like, let's say layers dot append, we need to use bottleneck, sorry, first we need to provide the layers, which will be the list, layers dot append this bottleneck, right? Bottleneck, we need to pass in channels, right? So first of all, in channels will be for first dense layer will be in channel as the same as the in channel as the input, right? So I'm just passing the in channels will be into growth rate, sorry, into, let me write it this way, it would be plus I into growth rate. Okay, so let's explain this what we had written here. Okay, so bottleneck layer, let's say first it is creating first layer of bottleneck, will receive some in channels, right? Let's say it is nothing but 56 cross 56 cross 3, simple, right? So now here you can see at here we will receive 56 cross 56 cross 3, simple, right? After that what we are doing, we will convert this in channel, at the end it will be converted into growth rate layer, growth rate, number of growth rate, right? So our growth rate is basically 32. So now the output of first bottleneck layer will be 56 cross 56 cross 32, right? So the next bottleneck layer will require the in channel would be 32, right? And the third bottleneck layer will receive the input of 64, because we concatenate this 32 with the previous 32, right? As we are here concatenating. So next layer will produce the output with concatenating 32 into 32. So it will be 64, right? 32 plus 32. So that what we are writing here, the I will start from the 0. For first we will not adding any growth rate, right? So it will be in channel would be same. Let's say 3. The next time it will be 32, right? So that code we had written here, like in channel plus I star growth rate. Okay, and let's pass the growth rate here. Okay, so this will create a number of bottleneck layers, right? And last we will use nn.sequential. Let's say, let me write here self dot dense block nn dot sequential, and it will take, let's say, star layers. So now we have sequential block or sequential model with multiple bottleneck layer. Now we need to write simple forward method. Forward, it will contain x, and we need to just return. Let me write return self dot dense block, right? And we need to pass x. So this is about the dense block and bottleneck layers. So dense block will contain multiple bottleneck layer. Here you can see the first dense block will contain 6 layer, another will 12, the next will 24, and next will 16. Simple, right? So now this is about the dense block and bottleneck layer. Now let's create this transition layer, okay? This one, which will contain 1x1 convolution and average pooling with 2x2 kernel size and stride 2. Okay, so now let's see class transition layer. Let's say transition only, right? Let's say nn.module define init self. What it will require? Again, in channel and out channel, right? Because it is nothing but 1x1 convolution and average pooling, right? So let's say in channel, out channel, let's call super transition self. Simple, right? So now let's see what it will have. So here if you see the same con block is used here, so we need to follow this path, right? Batch normalization, then ReLU, then convolution. We will use kernel size 1x1. So it will be, let's say, self dot batch normalization will be nn dot batch norm 2d. Let's say, yeah, batch norm 2d. It will contain in channel. Now self dot con, which is nothing but 1x1 convolution, right? Con 2d. And let's say in channel will be same, right? In channel, and out channel will be the out channel, which we will providing here, right? We will see what output channel we will pass in the transition layer when we create actual DenseNet class, right? And now kernel size will be 1. Okay, simple. So basically this 1x1 convolution is used to reduce the number of feature map size, basically, right? So we are converting in channels into out channels. The output shape will not change till here. Suppose we are receiving, let's say if in channel is 32, then we will receive 56 cross 56 cross 32, and let's say out channel is 16, then we just need to, this convolution block will do 56 cross 56 into cross 16 output, right? Still we haven't changed the output size from the 56 to 28. That would be happen by average pooling layer, right? So let's say self dot pool nn dot average pool average pool 2d. Okay, kernel size is equal to 2, and we will use stride is equal to 2. So it will convert our output into half size. For example, I'm just considering this sample. Okay, this is not the actual. So let's say 56 cross 56 cross, we are receiving here some kind of, let's say 196 for just simplicity. Okay, and now this average pooling will create the output of 28 cross 28 cross 196, right? And here the in channel will be, let's say here we are receiving output 56 cross 56 cross 380. Just for simplicity, I'm not using actual number which are in the paper or which we will get, but I'm just explaining this batch normalization is only providing batch normalization. This 1 cross 1 convolution will reduce this the number of features, or you can say out channels, to this out channel which we will provide. So out channel is reduced here, and this average pooling with stride 2 will reduce this shape of our output size, right? Let me erase this, otherwise someone will get confused, like we are not receiving this same output, right? So this was for only explanation purpose. Now let's write forward path, right? Let's say def forward. It will return self x, and now let's say x will be self dot convolution, and this one it would be f dot relu, and it would be self dot batch normalization with x. So same this, right? Batch normalization, then relu, then convolution. At the end we need to provide average pooling, right? Let's say self dot pool, and we will pass x, and it will return this x. So now we have all part of this network is ready. We had created the dense block, we had created the bottleneck layer, now we have transition layer as well. So now we need to create one class or one model which will combine all of this, right? So now let's build this. So let's say class DenseNet, here, okay. So let's say nn.module self, it would be init self. Okay, so now what are the argument we will require here? So first of all, number of block, how many dense block we require, right? So let's say number of block. The second thing, growth rate, so which will be, let's say 32 by default, okay. And this number of blocks will be list, okay, because if you see we have first dense block will create 6 block, second dense block will create 12 layers, and so on, right? So we will consider it as a list. This will be our integer, and number of classes for the last layer. So let's say by default it is 1000, okay. We are thinking like we are training the ImageNet, that's why class is equal to 1000. You can take any number according to your data set, right? So now let's first create super DenseNet self init, okay, right? So now let's start implementing the DenseNet using the blocks we had created, right? So first of all, let's say self.growth rate. Let me write like this, right? So it will be growth rate, okay. Now first of all we need to create this part, right? 7 cross 7 kernel size convolution with stride 2, which will convert the output size into half, and then max pool with stride 2, which will again convert the output into half size. So from 224 we receive 112, and then 56, and then our dense block we started. So let's first create this two part, right? So let's say self.con1 is equal to nn.con2d. we will receive in channel as a 3 because our input is into RGB 3 channel, right? 3, and now out channel will be, let's say 2 star growth rate, kernel size will be 7, stride will be 2, and padding will be 3, right? Simple. So this also is mentioned in the paper that first convolution block will contain 2 into growth rate out channel, okay. So let's say now self.bn1, which is basically batch normalization. Let's say nn dot batch norm 2d, it will receive the input channel h2 into growth rate, okay, because it will be followed by this convolution, right? So now self dot pull 1, the pull 1, because there are multiple block will convolution block and poolings are there, right? So we are now creating this one pooling 3 cross 3 and stride is equal to true. So now let's say nn dot max pool, sorry, it would be max pool 2d, and let's say kernel size will be 3 and stride is equal to 2. Okay, so this part is created, okay, and the ReLU of course we will use in the forward method, okay, because we need to use batch normalization, then ReLU, then convolution. We will write in the forward method. So these are the layer which we required to perform that task, right? So now let's create about the dense block, okay. So first of all, let's use number of channels, which is basically a in channel for the dense block, okay. So let's say it is currently 2 into growth rate, right? Let's say growth rate, simple, right? Now let's build the dense layer. So let's say self dot dense 1, which is basically a dense block. Let's say dense block, we need to provide number of block of 0. Let's say it is list, so let's say number of blocks, okay. The number of blocks of 0. So this much bottleneck layer will be created in the dense block, okay, and number of channels, which is basically in channel for dense layer, okay, for bottleneck layer, and then we will require growth rate, right? Simple. So this is about one dense layer. Now what we need to do, let's suppose after this dense block, what will be the output channel? So now our number of channels will change, right? Because in the dense block we are concatenating the output. So whatever we are passing, it is not the actual output of the last layer of the last bottleneck layer, or you can say the dense block output, right? So it will be changed by, you can say, let me write it like this, plus or equal number of blocks, how much blocks we are using depends on that, into growth rate, right? Sorry, let me write growth rate. So first dense block will create the output shape of this. So basically this is about the channel, okay. So here if you see this one, we are passing 56 cross 56 into 2 into growth rate. So basically our growth rate is 32. Then here we are passing as an input 56 cross 56 cross 64, where 64 is will be the in channel for this 1 cross 1 convolution. But it contains a 6th layer of bottleneck, so output will be 6 into number of growth, right? So now so we reach till here, okay. This part is created. Now the transition block will be there, or transition layer. So now let's call that. So it will be, let me write, self dot transition 1 will be transition, it will require number of channels, because the output of dense block will be as an input of transition layer, right? Number of channel, and how much we need to convert, it would be the half size, okay. So we are reducing here into the half basically. So let's say number of channels divided by 2. So after this transition layer, we are reducing the feature size by half. So our number of channels will also change, right? Number of channels will be this one, number of channels divided by 2. So we are using double slash to we get integer output, right? So this is the whole dense block and transition layer. So we reach at here, dense block 2, now we will create. So we had created this convolution and pooling, dense block 1, transition layer 1. Now we are implementing dense block 2. So this will be same, right? So let's say self dot dense 2 will be dense block, let's say number of blocks of 1, and number of channel and growth rate, right? Now let's say number of channels will be same. Let me copy this line, right? Number of channels here, it would be 1. The same transition layer we need to provide. Let's provide it to transition 2. Same thing. Now number of channel will also change, right? So I am just writing here, let's say dense block 1. Here we have transition 1. So you can relate with this table, right? So dense block 1, transition layer 1. Let me write here transition layer. Now this part is dense block 2 and this part is transition layer 2, right? Simple. Let me write this above. Okay, so now we had created 2 dense block. Now another 2 is required, right? So it will be the same for it as well. Let me copy it, right? And I will update whatever is required. So now let's say it would be our dense block 3. Here it should be 2. It is dense 3, transition 3. Here we require 2, and everything will be same, right? Same for dense 4. So if you see, after dense layer 4, we are not applying this transition layer, okay? So we need only this part basically. Let's say, sorry, it would be number of block 2, right? Now let's say self dot dense 4 is equal to dense block of number of blocks of 3, number of channels and growth rate, right? And number of channels will be changed as well after this dense block. And now we do not require this transition layer because they haven't used. So now they will use global average on a batch normalization and rest of the part, or fully connected layer, right? So now let's define, let me write it is dense block 4. Simple, right? So now I would need to create a dense basically batch normalization and fully connected layer, right? So let's say self dot, so we had created batch normalization 1 here. So now let's say bn2 is equal to nn dot, sorry, it will be batch norm 2d. Will create number of channels. Okay. Now last fully connected layer, right? fc will be nn dot linear and number of channels will be as an input channel. Of course we need to make it flatten. We will write that code in the forward method, right? And after that number of classes, right, which we had defined as 1000. Simple. So now let's build forward method. So till now we had created all the layer which are required to build this whole block, okay, whole DenseNet connection with 121 layer. So now let's define the forward method. Let's say first will be self, then it will be the x. Okay, so now first of all we need to perform this part. So let me write, let's say x is equal to self dot pull 1, f dot relu will be self dot bn1 and it will be self dot convolution 1 of x. So I just write in the one line, but you can think it is like first we are applying convolution. This convolution is this part. Then we are applying a batch normalization, and then we are applying the then we are applying the ReLU, and then we are applying the pooling part, right? This is the simple convolution block basically, and now we will implement a dense block. Okay, so now let's say x will be, so if you see, we need to create first a dense block, right? This dense, and it will be followed by the transition layer. So let me write self.dense 1, which will receive this output, and this will be provided as an input to the self.transition 1 layer, right? Let me write trans 1 and x. Same, we need to write self.dense 2 of x, and then it will be provided to transition 2 layer, right? Trans 2. Same, now third dense layer, self.dense 3, it will be passed to self.trans 3, which is transition layer. Now self.dense 4 and x, right? After that, we will require the average pooling and you can say fully connected layer, right? So after dense, let's apply the ReLU first. Okay, x is equal to, let's say, f.ReLU, which will be self.batch normalization, sorry, it would be bn2, and apply the x. Okay, so now what we are doing, we will create this 7x7 average pooling, right? So I will use adaptive average pooling, which will take as an input like in which shape we want our output, right? And it will calculate kernel size, or you can say stride by itself. So let's say x will be f dot adaptive, I'm not getting the suggestion, yes, adaptive average pool 2D, which will take this x, and we need 1,1 output size. So basically, let's suppose we are receiving here, let me share, yeah, so here we are receiving 7x7, right? So let's say at this stage we have 7x7 cross some feature size, or you can say number of channel. Let's say we have 128 channels here, okay? But in PyTorch you can consider it like this, right? Because it is channel first. So let's say you are passing this kind of input 128 cross 7 cross 7 here. So what it will do, it will convert this 7 cross 7 into 1 cross 1. So it will reduce the size of itself, the feature, okay? So, and it will return, as I mentioned, 1,1. So it will create 128, 1 cross 1, right? So after that we just need to flatten it, or you can say we are receiving just only 128 here, 128 you can say tensor with 128 shape. So this is done by the average pooling, adaptive average pooling, okay? So let's say 1 cross 1, this is done. Now let's say x is equal to torch dot flatten, it required x, sorry, I'm writing output, so it is not the output, it is basically x, right? X, and we need to provide the 1, simple, right? On which dimension basically we are doing. So it will be batch size comma 128 cross 1 cross 1, right? So which will receive batch size into 128 basically. So now x will be self dot fully connected layer, right? Which will receive the x and provide the output into number of classes, and we need to just return this, let's say return x. So this is about the DenseNet. Now let's run it. Okay, it looks good. Let's say DenseNet model will be DenseNet, and number of blocks we need to provide, right? So let's say number of blocks will be, if you see here, first we need 6, 12, 24 and 16, right? So let's say 6, 12, 24 and 16, and then growth rate is 32, right? So DenseNet will require number of blocks and growth rate, right? So now our model will be created. Let's see. There is average pool 2D unit got unexpected elements tied. Okay, so it should be stride. It is the typo. Okay, so let's go to the line number 7. I think where I written. Let me search. Okay. Okay, so where this line is before the forward, so it would be somewhere else. Average pooling. Okay, here R is missing. So I am very habitual to it, like typing mistake, right? Let's see. Okay, so it's working. So now let's plot this model with the input shape. So we will get, if there is something error, we can get that, right? So let's say I am using only that torch view, right? So you can see we had installed torch view and we are using draw graph. So let's say draw graph, we need to pass the model basically, which is DenseNet model. We need to provide input size. Let's say input size is equal to 1,3,224 and expand nested is equal to true, and now we need to visualize it, right? Okay, visual graph. So now let's plot the model. If we had written everything well, it will run. Okay, failed to run torch graph. See the error. Something is missing. Running mean should contain 1024 element, not 1280. Okay. At where we are receiving the error, let's see. So the above exception direct cause here. Okay, so let's see code one by one. If we had done some mistake, let's start from this part, right? This is nothing but just calling the forward. Let's see here. The number of blocks 0, growth rate, number of channels, number of blocks 1, 2, 2. Okay, so here it should be a 3, right? Number of blocks 3, here 3. I think I copy paste and made a mistake. Okay, so it should be number of blocks of 3. Now let's run it again. Hope it will work. Let's see if we had written a proper code or not. Let's run this. Okay, again we are facing some error. So torch does no attribute flatten. Okay, so f should be small here, right? Torch dot flatten. Let's see. I think now it will work because we had already reached at flatten layer, right? Okay, now yeah, it's working. Now let's see the model. Here there is a dense block. Okay, depth. Yes, so if you see here in the output, we are concatenating, right? So if you see here, there are 96 output, right? Now we have adding 32 in it. Now we are adding 32 in it, and so on. Same as a growth rate, right? And the transition layer will reduce the output channel, right? So let's say from first of all, convolutional will compress it 256 into 128, right? Then the average pooling will reduce this size 55 cross 55 into 27 cross 27, right? So this is about the DenseNet. If you have any query regarding it, you can write in the comment section. We can discuss there. And if you like my video, please press the like button and subscribe my channel for more content. Thank you.